All right, so quick reminder, Thursday will be your written test. I already confirmed the coverage for your test. So what we're going to cover today will not be covering the test, don't worry, but it's a very important topic. But I will walk you through. It's a tricky one, but I think it's a very interesting one. I'm pretty sure it's something you haven't really seen before, even though it's about sorting for graph. Okay, we'll take a look once we do some very quick walkthrough about what you should really pay attention to. Okay. So written test will be Thursday, and then the guide has been released. So make sure you study everything, starting from the beginning until slide number 75 for the graph lecture. It doesn't cover just about graph. You guys should really study everything that we have covered so far. But I think it will be a very good opportunity for you to study also for the exam at the same time because they overlap on the coverage. If you want to speak to me, I'll be available today during the office hour, or you can, if there's really something you think that can resolve over email, that's okay, right? Give it a try. And the tutorial video, the tutorial session from last Thursday is also on the lecture site, okay? There's something I really want to remind you guys as well. I'm pretty sure you're aware, but I just want to give you some tips, okay? All right, if you look at the calendar, we are now on the 16th right here, lecture 19, right? So that's what we're gonna cover today. And written test will be during the tutorial session this Thursday, that we know. And guys, please notice, the programming test number 2 will be next week. It's not that far away. To really make sure you can really also get prepared in time, I would suggest try to really get your assignment number 3 maybe after the test, or maybe if you're able to work on that just for 1 or 2 hours before the written test, that's even better. I'll give you the solution for assignment 3 earlier than usual so that you can actually study for that. Your programming test number 2 is actually going to cover both assignment 2 and 3 about the graph part. Okay, I'll give you some guide and let you know some ideas. I'm going to give some tips about preparation. That's something you want to get ready for. So the coverage for programming test 2 is actually quite different from programming test 1. In programming test 1, we try to do trees, rotations, but this time we're going to do graph. Okay? If you have been doing assignment 3, you'll get some idea about what kind of question that there might be. I'll give you more concrete tips in the actual guide. Right? I'm going to release it very soon. Also the solution for A3 as well. But you don't want to just look at the solution. You know that it's not the best way to get yourself prepared for a programming test. All right, so I think we still got quite a good number of topics to be covered before the end of the semester. It's not like after written test, nothing to be covered. Not really. We still got many exciting stuff. I'm still preparing some new stuff as well for this term. All right, you can look forward to it. Rather than doing recap, you guys should know where to study. Why don't we start with a new topic right away? All right, and let's start with this idea. It's called directed acyclic graph. You know every turn in isolation, but we're going to put them together and see why it could be very useful. So today we're going to do 2 examples in total on the DAC graph. It's a specialized kind of graph. I'll explain that first of all, and then we'll do 2 examples. The first example will be just like a standard. It's simply given some contrived example, just try to see what should be the mechanical process to perform some algorithm on the DAC. But the second example there is going to take us maybe more time. That one there is going to be tricky to understand, but it's a very practical application that we can also go through, right? So these are 2 examples we want to go through today. If time permits, I can also talk about why, in order to implement algorithm on DAC, you can only try to modify depth first search, but not breadth first search. That's something I'll try to cover either at the end of today or maybe in the beginning of Wednesday. We'll see. I really want to walk you through the 2 examples very thoroughly so you will know how to perform algorithm on the DAC. Okay? And the slides I'm going to talk about will be slide number 76, okay, over here. Let's first of all talk about definition for DAC. Okay, it's a graph, of course. Okay, let's talk about it. There are 3 components, of course. First of all, we're talking about a graph. And as soon as we talk about a graph, we know that it's going to have vertices and edges. Let's start with the basics. Okay. So we got some graph G, which can be defined by vertices and also edges, right? So this is the part you can understand about what is a graph in general. And then there are 2 specific properties. One is about direction, okay? That one there, here, directed. So that talks about directed graph, not undirected graph, okay? So here, so it is direction. And the simplest example would be, let's say we got two vertices. Let's say we got V here, and also we got U here. And then we have some direction between them. Let's say from V to U. However, this is something you have to also watch out. Direction here in DAC means something very specific to your application. I can tell you the principle, and then we'll see some example that's on the slides, and then we'll do one specific example also to begin with. Okay? So whenever you got a direction, it really trying to model some kind of dependency. Okay, so dependency here is really the keyword. So this means whenever you're, let's say beyond this course, if you're trying to build some application and you believe you want to use a graph, and you also believe that among objects of your system, they have some dependency among them. In that way, you may want to use a DAC. And then later on, topological sort, which we'll talk about, the standard algorithm, right? So dependency here is really the keyword, okay? There will be a different example here about DAC. So for example, this will be the most relevant to you guys about prerequisite. For example, 2101 should be taken before 3101. It's dependency, right? Or maybe you should really do certain task before you can do the follow-up task. Right? Maybe you should sort the array first before you can actually do binary search on the array, right? So there's some dependency there about actions. So prerequisite is one example. And also inheritance hierarchy, if you say from one subclass extends another another class. So between child class and parent class. That's what you learned back in 2030, right? Inheritance diagram. And also, if you want to do the scheduling between tasks, so this might be more like a 3221, your operating system class. So before, for example, I can enter into the critical section for the shared resources, I need to require or acquire some lock into the critical section. So for those of you who took operating system, you will know what I'm talking about, right? Just another interesting scenario, very, very standard. The next one there is about transactional updates. So for those of you who took a database course before, or maybe you will take a database course later, transaction is a very important topic about how you can somehow execute various updates as an atomic operation. They should really conceptually happen at one go. But in practice, we still have to schedule like a sequential composition of the updates. But how exactly do we turn from transactional updates into sequential assignments? That's something we'll see today. That's exactly where we can use DAC and also topological sort. So this will be the example I would like to give to you as the second part. Okay? That one will take some time to digest, but I'll try my best for today to walk you through all the specifics. Okay? Transactional updates. And there are many examples. You can just look it up to see topological sort and practical application. You will see many practical contexts out there. Okay? So these are the, okay, so that's about dependency. And one more thing. What does it really mean conceptually? When I have a direction between V and U, that means V should happen before U can happen in general. Right? Just keep that general concept in mind. Okay? So this simply means V must happen first before U happens. Okay, so we're following a certain order, V and then U, V and then U. All right, I think that's good for now. Okay, we'll see more example. Okay, all right, so that's about direction. And the final bit for the DAC is acyclic. There should be no cycle, basically. Okay, so that part there is straightforward. There should be no cycles. Basically, more like a tree in some way. However, I want to give some exercise for you to really compare. Okay, of course, this will be kind of beyond the scope for this test over here, but do some comparison maybe when you're studying for this lecture. Okay. So exercise for you to try it out. I want you to compare to see exactly what is common between these two and what's the difference. Talk about DAG, D-A-G, versus tree. Okay, they are not exactly the same, but they do share something in common. Okay, I'll give you a little bit of hints. So you want to go on these kind of criteria. about direction, and also about connectivity, and also about cycle. Okay, so these are 3 example criteria you can use to compare DAG versus tree. All right. And of course, for Thursday's written test, you should be able to answer pretty much already about, for the tree, what should you satisfy, right? That's something I'll leave to you. Okay. All right, so up to now, we talk about DAG. The acronym stands for Directed Acyclic Graph. And you know about 1, 2, and 3 ingredients for what would make a DAG. It's just a graph with certain criteria satisfied. Okay. Questions so far? All good? All right. And let's now give one example. Let's say curriculum, like a prerequisite between courses, right? Let's just have a simplified version. It's not exactly realistic, but I think that'll give you the idea, okay? Let's say many of you are from engineering. Why don't we say you start with your EECS? I'll just put a number here, but it's really EECS, okay? Let's say you start with the 1011 MATLAB, I presume. And then followed by that, you have 1021, which would be your first Java course. And after 1021, you enter your second year, you go for 2030. And after 2030, you go to data structure, 2101. And then only after you have completed this sequence here can you actually take 3101, right? Okay, so that one there will be 3101. 3101. Okay? Well, this is good. This is already a DAG. It's a graph, directed, no cycle, and also, yeah, exactly. It's a graph, directed, and no cycle. Let me make it a little bit more interesting, okay? Let's say we also got some math courses. Let's say before 2101, not only that you must have already taken 2030, you should also have taken 1019, right? The math course. Okay, let's put it there. So what we have is 1019. Okay, 1019 should also go before 2101. And let's say before 3101, you must have already taken, let's say, 1090. Right? I think that's good enough. You might be arguing, I agree. You may want to also take an arrow to say 1019 and then 1090. Let's not worry about it. Let's just leave with this, right? Simplified version, right? And one more. Let's say we can also choose to take some physics course, okay? 1801 and 1802, and that'll be it. And then we can consider this curriculum map. So we got here 1801 followed by 1802. Okay. Okay. Let me see if I can. Okay. This one is kind of annoying. Okay. Okay. So we got this DAG over here. That's the first example we have. All right. Good. And then let's just color the arrows. I want to color them so I can show you another concept. Okay, so let's say we got orange here, this one here, and we also got, let's say, green arrow here, green arrow, and then we got pink arrow. Okay, let me number them. There's a reason for numbering them, not really about chronological order, just about how I can refer to it, and then when we talk about about topological order. Okay, so we got 1, 2, 3, and 4. For the green arrows, 5, 6, and 7. That means we've got 7 dependency links that we somehow have to worry about whenever we want to suggest like a order. Okay, let me talk about that one. Okay, whenever you're giving a DAG, the follow-up question will be, we want to define something called a topological order. Okay, I'll write it down, and we'll see some example. It's called topological order. what the topological order will do is we said that it's try to turn your DAC graph over here, which is non-linear, right? We talk about non-linear versus linear, right? Graph is definitely non-linear. Topological order is a linearized version of your graph, but it has to satisfy certain criteria, and we have to know how to check the criteria systematically, okay? So topological order is a linearized version. Linearized DAC, okay? Linearized, which means we got to give a sequence for the map, okay? And you can think about, let's say, when you actually apply for graduation, the chronological order of all the courses you have taken, that one there should really be a linearized version of the DAC for your curriculum map. Because you got all the prerequisite, you want to make sure you always take the prerequisite before you can take the follow-up course, and before you can take the CCRO, right, etc. Okay, let's see one sequence here, okay? So let me start with this. Let's say I start with 1801, 1011, and 1021, 1019, and then 2030, 1090, and then 2101, 3101, and then 1802. All right? So this will be a legal topological order, okay? But how do we check? Exactly, right? So the idea is you somehow have to identify all the valid edges between pair of vertices. For example, 1801, 1802. These are two vertices you can see from the sequence. And there is an edge in the corresponding DAC right here. If there's an edge, you can put a check mark. So you satisfy that. All right. On the other hand, for example, if I put 1802 and then 1801, in that way, it's not really satisfying this particular constraint, right? So that will be illegal, okay? So what we'll do is, first of all, 1801 and then 1802, okay? So these are the two. And then, because there is an edge between them, I'm just going to link them. And that's corresponding to number 7. So that particular constraint is satisfied. Okay? And then let's see more, right? Just be more thorough. And then we'll try to formalize it, right? Like in general. Okay? Also, I have, for example, this will be 1011 to 1021. And also 1021 to 2030. 2030 to 2101, 2101 to 3101. I basically cover 1, 2, 3, and 4. Right? Okay, let's mark them down. So what I have is from here to here, this will be number 1. And from here to here, this will be number 2. And from this to this, it will be number 3. And from this to this, it will be number 4. So 1, 2, 3, 4. Okay. And then we can also see, let's say 1019 and 1090. Okay. Oh, for example, this one here, 1019 to 2101. Okay, we can definitely see that. 1019 to 2101. Okay. 1019 to 2101. This is 5. Remember the meaning of an arrow. For example, 1019 must occur before 2101. In this sequence here, 1019 indeed occur before 2101. If I swap the order, it's going to be illegal, right? Okay, and also we got 1090 to 3101. Okay, so we got 1090 right here to 3101. Right here. Okay, this will be number 6. Okay, we got all the 7 here. So this means, let's say for this particular arrow, for example, you can see that we 1802 can only be completed after 1801. However, in between them, we didn't really say how many other courses you might put in the middle. It's not really constrained in this particular DAC, so that's okay. Right? As long as 1801 occur before 1802, somewhere in the sequence will be okay. Alternatively, I could have put maybe 1801 here and put 1802 here. That's just another possibility. Right? So that means you got more than one legal topological orders given your DAC. Right? So not unique. Not unique. That means many legal alternatives exist. Alternatives exist. Okay. Question so far? Of course, one very typical question could be, I might just give you the DAC, and then I might just want you to figure out, give me one example topological order. That should be easy, and then justify it. Or I can give you some order, and then I want you to justify if that's a legal topological order. That's another part. Yeah, Diego.
Is there a way to know all the possible combinations that would be legal?
I know where you're going. It's not as straightforward. I would say at this point, let's not worry. Okay. I will try to see if we have time or maybe some space to cover that part, but it's quite sophisticated to figure out. I mean, in some cases, it may not be even possible when your DAC is actually too complicated, right? So here, I got just a few vertices. There are not that many. But when you got so many, it may not be so useful for you to know how many maximum you can get, right? But let's just focus more on, if you're given an order, how can you check it? And then, also how you can do the topological sort, okay? All right, so next question is, how can we formulate about this part here, right? How can we formulate it, okay? So let's now talk about it, okay? Let me just copy this, okay? And then I will get to a new page. Okay? It is the predicate you actually saw on the slides, but let's now try to formulate that, okay? We're basically saying between any pair of vertices, if they correspond to an edge, then that edge must be such that the origin of the edge must occur before the destination. Okay? So to formulate, okay, let me write down the idea and then we'll look at the actual formula. Okay? So here's the principle. Given any edge, let's say U and V, that's a valid edges. For example, you can see 10, 11, and 10, 21. That's one valid edge, right? We're going to identify every pair, okay? If U and V exist in the order, then the origin must occur before the destination. Then U, the origin, must occur before V, the destination, right? Origin. Okay, let's see how we can do that. And to really help our formulation, let's put some indices for the actual vertex that we can refer to. Okay, let's say we have some indices, index, like an array. Let's say the index will start with 1. That's actually the convention I do in the actual slide. You can put 0 if you want to. Doesn't really matter. Okay, so here let's say index 1, 2, 3, 4, 5, 6, 7, 8, and 9, right? We got exactly 1, 2, 3, 4, all the way to 9. And of course, in general, it could be just n indices, right? Okay, so now, given an order of length n. So that means we got vertex 1 all the way to vertex n, right? So we got vertex 1, vertex 2, all the way to vertex n. And then we want to say that for every combination of two vertices we can find in the sequence that correspond to some valid edge, it must be that the one that occurred before is the origin. The one that occurred after will be the destination. Okay? That's something we have to specify. Okay? Let's look at the actual formula, right? This one could be tricky, but you definitely gotta make sure you're convinced when you study for that. So we say for every pair, let's say I and j, the two indices. For every I and j, and there should be valid indices between 1 and 9 in this case, but I can say 1 and n. Okay? So 1 less than or equal to I less, okay, I'll just say I and j in between. And you can say I is not equal to j, right? We don't really allow any self edge, which will create a cycle. And also, the vertex of I and the vertex of j, this pair will correspond to some valid edge. Okay? This part here is actually very important. Okay? You cannot just find any two vertices, but they don't really correspond to any edge. For example, if you find 1801, 1011, there's no edge. Right? You can see 1011 and 1801, there's no edge. So we don't really consider that. Right? Okay. And if that's the case, we want to say that the origin happened before the destination. Right? How do we say that? Well, the actual order here is really about the chronological order because 3 must occur before 4, and 5 must occur before 6, and etc. So now in this case, we can say I should be strictly less than j. All right, so that's the very simple formula here, but you do need to look into it and see why it should be defined that way. But you can definitely just use that particular order over there to figure out. Okay? Any questions so far? Okay, let me recap very quickly. And then we got to get to how we can make use of the DAG. Okay? Now, I want to talk about one more comparison. Just before that, a quick recap. We'll talk about DAG, just a graph with direction and also no cycle. And it is possible for anybody to suggest to you some topological order, which is just a sequence of vertices. You're asking whether every pair of vertices in this sequence here will satisfy the constraint that's specified in the DAG, the dependency. That's the question. All right? Let's do one more comparison, and then we can get to the actual algorithm. Okay. This one here just basically showed to you, you actually have different alternative for the topological order. Yeah, question. The capital I? Let's see. Jada, this one here, which one? Capital I, you're talking, is it last line? Oh, that's 1. That's okay. All right. All right, just in case. Because 1 will be the minimum index, right? Just think about this minimum index, that's a maximum index. We just try to index the vertices, okay? Okay, let's look at this one here. I just copy this order here into right here. We know that this one here is legal, right? Let's think about if I try to somehow move around some vertices in the legal order, I can generate just another legal order. Right? Let's take a look at that. So this is something we know as to be legal, okay, from the previous page. So this order here is known to be legal. What we want to do is we want to move around some vertices while we can still satisfy all the constraints. Okay, let's see. If you compare this order here and this order here, they're pretty much the same, except for one part. Okay, let's now take a look. So it would be for this part here. That's not exactly the same. Okay? You can see that here I got 1011 followed by 1021. But here I got 1011 followed by 1019. And then 1021 followed by 1019, 1021 followed by 2030, right? It's not exactly the same. Right? So that's the difference. And then for all the rest, this part over here and this part here, they're identical. I just want to show to you, by moving around the vertices, we can still argue by some local changes, you can still argue about globally, it is still a valid or legal topological order. Okay? Let's now take a look, right? The way to argue is to look at all the edges you can identify in the links, okay? So for example, you can see here we got 1011 to 1021, right? Oh, let me just show to you here. So we got 1, 2, and 3. Okay. 1 here. Is 1 still there in the new order? So we still got 1011 to 1021. As far as this link is concerned, we are fine. Okay. And then we also got, let's say, from 1021 to 2030. Number 2. So 1021 to 2030, right? So this is actually very important for you to see. In order to satisfy, let's say, number 1 here, I can either try to move the two vertices consecutively, adjacent to each other, or I can try to do 1021 followed by something not part of the constraint and followed by 1021 itself. It's actually okay, right? That's the main point I'm trying to convey to you, okay? And then we also got from 1019 to 1090, right? So this one here is number 5, okay? Number 5 over here, okay? Oh, do I have 1019 to, I don't actually. I beg your pardon, I should get myself confused. Okay, this one is fine, okay? And then we also got 2030. Also, we got 2030 to 2101. And again, sorry for the confusion. Okay, and then we got 2030 to 2101. Okay, 3 here. All right, so all the 3 links are preserved. Okay, that's the main point. So what you can try, maybe with that particular block, are you able to find other alternatives that can generate more legal topological order? Right, that's something you can give a try. Okay, just manually. You don't need to do it systematically. Okay. Okay, little exercise. Produce more legal topological order by moving around vertices. Okay, that's good. All right, so let's now, before I talk about that algorithm, right, and then I think I wanted to talk about topological sort. Okay. Okay, so far, what we have is we have a deck directed acyclic graph, and let's say taking that as an input. And by running some algorithm, we can somehow generate one legal topological order. A legal topological order. The process is called topological sort, right? That's something I kind of mentioned in day 1, but now we can really see that in detail. Okay? So this algorithm over here is called topological sort. It's really about sorting dependencies. It's not about sorting from from random orders into non-descending order. Not really. We're not talking about like a merge sort or quick sort, selection sort, insertion sort. Not really. Okay, we're talking about sorting dependencies. Okay, sorting based on the dependency links. Dependency link in the input deck. which is right here, okay? And we'll see the next page. But topological sort is very similar to a depth-first search. We're going to see later why using a breadth-first search cannot really give you the topological order that's going to be legal. We'll talk about it a little bit later. So topological sort. It will require just a little bit of extension to the depth-first search. We'll see that. Okay? There will be some slight extension to depth-first search. On the other hand, let me also make it very explicit. If you try to use a breadth-first search, doesn't matter how you try to extend it, it's not the way to go. Okay? Breadth-first search cannot achieve this. It's more to do with about the order of backtracking of the vertices, right? When you study for the depth-first search, one important keyword is about backtracking, where all your incident edges have been already marked, right? So the current vertex can just be backtracked or removed from the stack, right? That's something we spoke about when we discussed depth-first search, okay? Depth-first search, all right? Okay. All right, any questions so far? Okay. Why don't we take an earlier break today? I still got about 1 minute, about before halfway. Why don't we take a break now? And then after the break, I want to talk about the algorithm in general, showing you some Java code, and then talk about running time, which is very straightforward. And then we'll do examples about topological sort. Okay. So this will be the implementation for topological sort. It's very similar to what we spoke about earlier. So in general, by doing a single depth-first search, you may not be able to reach out to all the vertices that's reachable from the start vertex. So you may have to run a loop to get multiple depth-first search to be done, right? That's something we kind of spoke about earlier. So it will apply to the topological sort. Okay, let's look at that. We got two methods in total here. So we start with topological sort. That's the top level method here. And then inside the loop, we're going to call a helper method. That will be the depth-first search. And I have a subscript topo. So that's kind of modified version of the depth-first search, slightly modified. Okay? And the helper method is defined right here. So this is saying, as long as we got another unvisited vertex in the graph, pick it, and then start from there, do another topological sort. Keep doing it until all the vertices are covered. Okay, I'll write it down. Okay, it's a very critical insight right here. Okay. As long as there is an unvisited vertex, choose it, and perform a run of the depth-first search, the modified version for topological sort. I'll go over that with you very quickly. Okay. Using it as start vertex. Right? For example, you can see V here is unvisited. We just use V as a start vertex. Right? So this part here is basically just about performing depth-first search. Right? For that part there, I'm not going to bother you. That's something we learned in the previous lecture. Right? And also for your assignment number 2, the solution, you will also see something very similar as well. I just want to point out to you about how we can figure out the running time for topological sort. Okay? It's basically just about doing depth-first search. We said that usually if you're only doing some reasonable extension to depth-first search or breadth-first search, if you're trying to push and pop every vertex only once, you never try to redo or reprocess every vertex. In that way, it should be proportionate to the number of vertices plus the number of edges. Right? So that should be the running time. It's really the case for topological sort. But I'm going to highlight some lines. Okay? So there will be a stack you have to use for the topological sort. Okay? I'll highlight in, let's say in green, first of all. Okay? So what we have is, we have some stack right here. Okay? Hey guys, please. All right. Thank you. Okay. And then we got some push. Okay? Initialize some empty stack, and then we got push. Okay? And then we check to see whether or not the stack is empty. So for the current DFS run, as long as the stack is not, as soon as it becomes empty, that's done, right? That's what we learned earlier. And then we also got, every time, once you identify the top of the stack, right? Of course, you can try to look at what's the top of the stack. And you're going to figure out all the outgoing edges from the top. It's like incident edges, really. I want to reach out as far as I can, right? And then we're saying that as long as we have more edges that can lead us to something that's unvisited, we should really keep going, right? And of course, if the, okay, I'll draw a little bit visualization for you, but that's something you can also see from the code itself. So currently, we are looking at some E over here. So think about if this is the edge we're looking at right now, and the opposite, which is what we call. If this one here is unvisited, so that means this one should be a discovery edge. In that case, we have to also push that onto the stack, right? That's something we did earlier, okay? And then we can push that onto the stack, okay? So when should we backtrack? Once we have handled all the incident edges for this particular vertex, then we should really backtrack, okay? About all incident edges processed or marked, okay? In that way, we're going to pop it off, okay? So these are all the lines relevant to stack manipulation about pushing, popping, etc., right? So every vertex will be push and pop exactly once. So that tells you the running time should be just proportionate to the number of vertices, number of edges. Okay? So that's the main point I'm trying to make. Okay? So if you try to look at the pushing right here, okay, you can see this is the push line over here, and this line here is a pop line. Okay? We're doing that exactly once for every vertex. Okay? Each vertex, push and pop, only once. That tells us the running time is going to be go of the number of vertices plus the number of edges. There might be some constant, multiplicative constant, but that's something we can drop anyway. Okay? So that'll be the running time. Okay? And then, one more thing to say. This line here, it's about the actual topological order that we're going to return at the end. I'll show you exactly how this order can be manipulated. Okay? You can see that order here. First of all, you created that order right here to be empty. And call by value, you pass that to every call to the depth first search, which means we never try to recreate another order objects. Always the same object by call by value. Always the same copy. We'll keep accumulating. We'll keep accumulating this order objects. Okay, we'll see exactly how that can be traced. And finally, this line here. Whenever you try to backtrack a particular vertex, which will be the top, you simply just add it. However, notice one thing here. We're saying add first as opposed to add last. Okay? So here, notice that here is not add last. That means we're going to create a reverse order of the vertices that's being backtracked, not exactly the order. I'll write it down, but that's something you will also observe when we do the tracing. Okay? The topological order is the reverse of vertices backtracking. Okay? That's something we'll see. Okay? So I'll just highlight this one here. That's something you can also make sure you observe when we do the tracing. Okay? We're basically just going to do multiple depth-first search. And then every time for the depth-first search, we're going to accumulate certain vertices backtracking. And then we're going to combine all these order together. And the result will just be the topological sort result. Okay, we'll see. Okay. Okay, example number 1, contrived, but I think that will really show the idea. Okay. Oh, one more thing to say. Okay, I forgot. And every run of the depth-first search is going to give us a tree called a DFS tree. All right. Each run will give a DFS tree. Okay, we'll see exactly how that will look like. Okay, let's say here, first of all, the input here is a DAG. Right? You can see the graph. First of all, you got vertices, you got edges. Also, you got directions for every edge. So it is directional. And also, there's no cycle. You can also verify visually. Right? It's a DAG. What we want to do is we want to perform a topological sort on this. And we are making some assumption. Let's say the order in which we visit the incident edges will be alphabetic, right? Like before. Okay, let me just write it down, more explicit. Let's say we assume incident edges visited in alphabetic order. Okay, important assumption. Okay, if I somehow modify the order in which you visit the incident edges, you might just change the order that's produced, even though it's legal, but just different order. As we said, the legal topological order will not be unique. Okay, it's going to be most likely many alternatives will be there. The starting point is also very important. If I simply start from here, the depth-first search can just manage to cover A, B, C, D, E, F. So a single run will be okay. But I'm going to make it a little bit more interesting for you, just more general. Because in general, you simply don't have the graph in front of you visually. So you got to start with something. Let's say we're going to start with vertex E to begin with, let's say. So that'll be iteration 1. Totally possible. As long as you can choose a vertex that has not been visited yet, it's a valid starting point. Okay? Let's say we start with here, E. Okay? And then this will be iteration number 1, like a depth-first search, run number 1. So iteration number 1. So we're going to call DFS topo, the modified version. And then we're going to start with vertex E. And then the order array list is going to be empty in the beginning, right? And the list over here is going to be accumulated every time. Right? It's going to, if you require multiple runs for the topological DFS, we're going to keep accumulating, right, to cover all the vertices. Iteration 1. Oh, let's do topological sort. Okay. All right. So here, let me just write down directly the result. Well, we can do a little bit here. I start with E. And then I should go to D first. And D will be backtracked because there's no incident edges. So D should be pop. And then I go back to E. And from E here, I go to F. And for F here, I can also backtrack. And then I go back to E. Here, I have handled all the both incident edges, so E can be backtracked as well. And that's done. It's a depth-first search, right? Okay. Let me write down the result here. Again, let me just repeat again what I just said. I start with E, and then I go to D. Okay, let me just also show you the push and pop. I think that'll be useful. Okay, so we got push and also pop. E and then D. And for D here, nothing else to handle, right? So D should be popped. And then we go back to E. And for E here, I go to the other incident edge. So I should really push F. And for F, nothing else for me to go further. So F should be popped. And I go back to E. For E, both incident edges have been handled, right? And then I should really go for E. So far so good? Okay. So that means after this particular run for the depth first search, I will be able to cover, starting from here, 1, 2, and 3. Not exactly all the vertices in the graph. So that means we might need just, and we for sure we need at least another depth first search. But before that, let's recall this line. Every time I have the top of the stack to be popped, I need to add first into the order list. Let's see exactly how to do that, right? So if you think about the order, which is the array list, the first one being popped is D. Add D as the first element to the empty list. I got this. And then the second one to be popped is F. Add this not at the end, but at the front. Add first, F. And then for E here, like that. So EFD will be the final order I have so far. Guys, let me say one more point. That's also very important. You can see the pop here shows to you about the order in which we backtrack the vertices. However, the actual topological order for this part over here is the reverse, which will go for E and then F and then D. Okay, I'll write down just for the first time. This will be the reverse of backtracking. All right, so far we got this order here, and then call by value, we are actually going to pass this order here as the second argument for the second iteration, right? Let's say for the second iteration, I want to start in B, let's say, okay? So I'm going to start with here, B, all right? Oh, another thing to say, sorry, just before I forget, you can also think about from the first iteration, this part over here is the first DFS tree we have. Oh, just one moment. Let me finish that, and I'll take a question. This is the DFS tree, number 1, formed by the discovery edges. Yeah, question?
Is there any method that you're using to pick the starting vertices?
Oh, it's a good question, right? So I would say, let's say it doesn't matter which strategy you're using. We got 3 strategies so far. Remember, we simply keep a linked list of the vertices. You can think about you always start with the first. But there's no guarantee about which one might be the first one. So you can think about we just go over the vertex one by one. And then as long as the current one is not visited, start with that. Yeah, good question. Good. All right, let's now start with B. And then let's set it up, okay? Be careful. We try to build a foundation here about performing topological sort. So when we get to the second example, conceptually it's much more demanding. So we can be a little bit easier on this mechanical process. Okay? Iteration number 2. Iteration number 2 is going to be another run of the DFS, topological sort. And then this time we're going to start with B, right here. Start with B, and then the order we put over here, think about we're just doing call by value, passing the reference here. But conceptually, it's just like an accumulated list so far. That one there is going to be E, F, and D. So think about the result from the first iteration is passed right here. E, F, and D, right? We're accumulating. And then let's now take a look. the result. This one should also be very easy to see. I start with B. Okay. Oh, let me also say push and pop, right? Let's be 100% complete. So we got push here, and we got pop over here. So we push B, the start vertex. And then you got basically either go to C and go to D, right? But we don't really need to go to D anymore because D has been visited. It's not discovery edge. What kind of edge should it be? I'll leave that to you, right? That's something you should know from your study for written test. Okay, so we go to C. So we go to C here. Go to C. And once we go to C here, you can see C only got one incident edge, but that one there is not a discovery edge, so we should backtrack, right? So that means backtrack C, and then removed. And then we go back to B, and for B here, both of them have been visited, so backtrack again. So C and B, okay? So up to now, we have visited B and C. And what should be the order of the topological sort for this run? It should be the reverse of the pop order goes like this. So it should be the reverse, B followed by C. Okay? So thinking this way, I'll run it in front of you. What's happening here is when I got the order, I start with the iteration number 2 with E, F, and D from the previous iteration. And then the first one to backtrack for this iteration is C, at first. And then at first again, B and C, all right? B and C. And that will be the part we accumulated from the second iteration. So that's the result so far. Are we done? Not really. One more, right? So that means we're going to continue, okay? Let's say this time the start vertex will be A. That's the only choice we have. So this one here is going to be A. And this one here, let's still write it down, even though it seems to be so trivial. So we got iteration number 3. So we got DFS, topo, and now we start with A. And then the order that we're given will be B, C, E, F, and D. Okay, that's what we have. So this is the part from the first iteration, and this is the part from the second iteration. Okay, and we're starting with a different vertex, A. A here and B here. Okay, so we'll start with A. All right, so this time it should be rather straightforward. Just A push and then pop right away, right? Because once we push A to the stack, it becomes a top. But all the incident edges will simply lead to visited vertices already. So pop it right away. And then make sure you insert A also to the order, right? So what we have is, we have our stack, push A, right away, and A has these two incident edges not leading to any unvisited vertex. So we're just going to pop it right away as well. Okay. So that one there is going to be pop it right away. Okay. So the final order we have is going to be right here. We used to get E, F, D, and then B, C, and then we get A. Okay. So third iteration, first iteration, and second iteration. So this will be the final topological order to return. Okay. This will be the ultimate topological order to return. Okay. Guys, any questions about this? Right? It's a very thorough tracing just to show to you, you might need multiple depth first search to really cover all the vertices. So let's say in the test or the exam, I might say perform the topological sort. In that case, visually you would know which one to really start with. In this case, you might just start with A. You might just require one iteration. But in that case, it will give you the same order because you follow incident edges in the same alphabetic order. So give you the same order. On the other hand, I might say start with maybe vertex E, and then vertex B, and then vertex A. In that way, you also got to show to me about different iterations. What's the intermediate orders as well? Diego, got a question?
So my first question would be for the runtime of the worst case scenario. Wouldn't it be a little bit smaller than a regular DFS because of the fact that this has to be an acyclic graph?
No, actually, the running time for topological sort, even in this case, even though we need 3 iterations, right? You can see the very first iteration, the blue ones, only cover 3 vertices. You can think about it's with 3 pair of push and pop. And then the second topological sort run for the depth first search will cover only the 2 green vertices, which will be B and C. In that way, we also got 2 pairs of the push and pop, and etc. So overall, if you add them up all together, you got the number of push and pop only proportional to how many vertices you have in the graph. Right.
I remember in DFS there was a case in which if you have every single vertex connected to every single other one, like a complete graph, then it was bigger.
Yeah, I see what you mean. So I think, yeah, I see what you mean. You talk about like a complete graph case, right? Yeah. It's a slightly different angle. I can talk about it very quickly. It's a good question, okay? So here, what we said about V plus E over here, this is true in general. What you're saying here is, if the graph itself is complete, let's say, then we might be able to simplify this expression. I can write it down, okay? So this is true, for sure. Let me give you an analogy. When we talk about, let's say, the heights of a binary search tree, right? We say that it's H. However, H itself, depending on how balanced it is, it could be log n or it can be n. Similar here. Right? So here we're always okay to really have, oh, again, guys, sorry about that, this thing here that's blocking, right? I'll try to fix it maybe next time. Maybe too late for today, okay? Anyway, so for this part here, this is true for every graph. However, in the case where the number of edges is just about V squared, in that case, you can combine these two and reduce that to be V squared, right? But you can only reduce to V squared if you know for sure it's complete graph. Okay. I like that. Okay, so reduce to big O of V squared if the graph is complete. Okay, nice. Okay.
Second question is, I know we're seeing topological sort graph DAB, but is it possible at all to also make a topological sort of a complete graph?
Is it okay? Sorry, is it also possible to do topological sort on?
On a complete graph, a graph that has cycles, for example. Is that doable or not?
Well, of course. Well, the thing is, you can think about the topological sort itself. The graph, the algorithm is more like a depth first search. But if you apply that into a graph that has cycle, in that way, well, think about it, it's really like this semantically. The reason that we want it to be no cycle in DAG is because we don't want to have any circular dependency. If you got circular dependency, in that way, you semantically just don't know what to do when you got it in order. So that's why we don't want it. Right? Let me write it down. I think that's a good point. It's more at a design level. You can still apply topological sort on some graph with cycles. It's just that you wouldn't get any meaningful result from there at a design level. Okay? Good. I like that point. Good. So here, let me just go back to our introductory page over here. So the reason that we wanted to have no cycles is we want to have no circular dependency. No circular dependency. Okay.
My last question.
Go ahead.
How will you characterize the running time of the at-first operation for the array list? Because on each iteration, it seems that it really depends on how you practice.
Yeah.
And also your starting point.
I would say array list, of course, let's not talk about the actual implementation. It might be something very maybe efficient. I don't know, maybe they're using, we can look it up in the Java library. So let's say maybe it does not need to be array list, it could be a linked list, in which case at first will be big of 1. Yeah. So of course, I'm making some assumption that the array list operation here is big of 1, right? Yeah, exactly. But if I somehow give you an array, like primitive array, then at first could be big of n. That will destroy everything, right? Yeah. Okay. Guys, we got 10 minutes, but I think I can set up some context for the second example, right? To really fully do it, we might need to spend a little bit over to Wednesday. But I think it's an interesting example, okay? So this mechanical process about topological sort, if you're able to, just spend about a few minutes or 10 minutes to make sure you're familiar with it. So when I talk about that, more advanced example on Tuesday, the solution part, you will actually follow it. But let's talk about the problem itself. Okay. Let's get some background done first. All right. This is what I talk about as a transactional updates. Okay. First of all, let's do some, just understand what's going on here. You might see, you didn't, this is not a typo, I got C prime versus C. It's intentional, okay? So here, and also you can see conjunction over here, as opposed to maybe like a semicolon, right? There's a reason for that. So what I'm showing to you here is called a specification. It is called a specification of transactional updates. Which means when I specify this, I'm not really thinking about in what order should I really evaluate each of the constraints. I'm thinking about these constraints should satisfy at the same time. That's what I'm thinking. So this is more like at the specification, not implementation level. Okay? And the transactional updates are as constraints. Or you can think about parallel constraints. Parallel constraints. Not variable assignments. Okay, let's get this one clear first. Okay, so we talk about parallel constraints. We got conjunction over here. And let's also clarify what do I really mean by, for every variable we got A, B, C, D, right? You got A, B, C, and D. What do I mean by on prime and prime? So there's some meaning associated with it, okay? So let me draw some diagram to show to you, okay? Let's say we want to perform some transactional updates. So we talk about the variable values before the updates and after the updates. So let's say this is the transactional updates that we want to perform. And we say that all the variables before the updates, I call that the pre-states, before, okay? This is called the pre-states. In which case we got A, B, C, and D. After the updates, I may modify some or all of them. It's called the post-states. It's like a precondition and postcondition. Precondition should be satisfied before the algorithm is executed, and postcondition should be satisfied after the algorithm is executed. Okay, so this part here is called the post-states. In which case, we got A prime, B prime, C prime, and D prime. Okay. And the actual transactional updates here is specifying the post-state value of C should be equal to the pre-state value of D plus the, okay, sorry, let me go to the right order, okay? The post-state value of C should be equal to the post-state value of B minus the post-state value of A plus the pre-state value of D. That's how you interpret that. Or do one example together, okay? Let me also write something down, okay? And I'll get there a little bit later. So transactional update is actually very important because we are really trying to specify over here just about intent rather than evaluation order. It's really about the intent we have rather than evaluation order. Okay? Let me just do one example, right? We got 5 minutes. Should be good. Okay? Take a look at this. Okay? I simply copy this transactional update specification right here. And then I'm asking the following question. This is specifying some intents. And this is what I decide to implement. So I'm just using call and equal just to explicitly distinguish. Call and equal simply means variable assignment. Okay? I'll write it down. So think about right here. The conjunction over here. So these are the logical operators. And there's a very important property for logical operator. It's called commutativity. Okay, anybody know? Tell me what commutativity really means. What do I mean when I say an operator, it commutes? You can put in the layman's term. I'm just trying to be academic here. Yeah, go ahead.
You can change the order.
Yeah, I agree. Change the order. If I say P and Q and P, they are the same. All right, very good. Okay, they commute. For example, when I say P and Q, the same as Q and P. So that means my specification here, the order doesn't matter. I can swap the order in whatever way I like. Okay? But this part here is about how I want to somehow implement this in some programming language. And that program there is going to use assignments, variable assignments. This part over here is about programming operators. They do not commute. Meaning that if I try to do this assignment here first versus if I try to do this assignment first, it's going to make a difference. Why? For example, here C value is already changed. So the C I'm referring to here is really about the updated C. If I swap the order of these two, it's going to make a difference, right? It's going to give me different result. Just an idea. So now we want to really somehow, given the input as a constraint, logical constraint like a transactional updates, we would like to generate one valid way to implement it. On Wednesday, we're going to dive into this, of course, very deep about topological sort is the way to do this. But before we can even do topological sort, you want to somehow transform the transactional update, the blue part here, into a DAG. How do you do that? Right? Can we just do one more thing? Okay, let's see if I got time. 2 minutes. That's good. Let's now consider conceptually. Let's have some valid answer, the expected outcome. Okay? Let's say the following. In the pre-states, let's say we got A, B, C, D. I'm going to fix these values arbitrarily, so we'll start with that. Let's say A will be 1, B will be 2, C will be 3, and D will be 4. All right? And then I'm going to look at the correct post states. All right? And I'm going to do in this particular order. Okay, there's a reason for that. I want to start with the evaluation of the post-state value that depends on the minimum number of post-state value from others. In this case, I should definitely start with D, because D prime here only depends on the pre-state value of A and C only. It doesn't involve any post-state value. So I start with that. Okay. So I'm going to start with D prime, which will be, let's now do the replacement. A pre-state will be 1, C will be 3, 1 plus 3 plus 5, 9. D prime here is 9. Okay, what's the next one I should do? D prime is now done. The reason that I do D prime first is because it only depends on pre-state value. I don't see any dependency of the post-state value there. What will be the next one? Give me 1 minute. Okay, yeah. Yeah, because over here you can see A prime depends on A pre-state, but D prime, we just got it. Okay. So here, I got A prime. So D prime is already 9. And A in the pre-state is 1. 9 plus 1, I got 10. Right? So A prime will be 10. All right, the next one I can do, so A prime and D prime are already there. So now the next I can do B prime. So A prime is 9, D prime is 10. Multiply, I got 90. So B prime will be 90. And then finally, I got B prime will be 9, A prime will be, B prime will be 90, I beg your pardon, 90, and then A prime will be 10, and then the D in the pre-state is 4. Okay, 84, all right? You might be wondering, how did I know the order of doing this in general? Topological sort. That's something we'll see on Wednesday. All right, so guys, make sure if you can just convince yourself this will be the way to really generate a post-state value. And then we're going to show you that this one here, just by getting rid of the prime here and do that particular order, is going to mess up everything very badly. And we'll see the actual solution. Thank you. I'll see you on Wednesday.